Hi, welcome to lecture 5. In this lecture we're not going to learn anything fundamentally new, but we're going to apply what we've learned so far and solve just one, but one fairly extensive problem. And in the process we're going to pick up on some techniques that apply to problem solving in physics more generally. When you're solving a problem, you're really applying the rules of mathematics, the laws of physics, and so on to a particular situation. So one would think that doing it is a fairly logical process, and to some extent that is true. However, at the same time, physics is much more a craft than people think. So a lot of it is learning the skills, like the same way you might learn masonry or fine art or something like that. You have to learn the skills, you have to learn how to use the tools. And then on top of that, you need to develop a certain intuition for certain types of problems. Have a certain ingenuity about some of them, although there are a lot of very basic principles you can apply that will solve most problems for you that you might encounter in this sort of course. But it is a craft, it is an art, because we as human beings aren't rigorous logical machines, and while the subject area, the mathematics, is rigorous and logical, we as human beings are not. And so we have to learn that, and we have to train our brains. So in this lecture, there are just some points that we'll be thinking about as we're doing that problem. We're going to see in a minute. So one thing we're always going to do is we're going to define the variables we're using. Don't just write down x plus 3 equals, like if you haven't defined what you mean by x. Right? We're doing physics, so we're talking about physical quantities, not some abstract mathematical objects. We're just using those abstract mathematical variables, objects, so on, to help us make sense of the physical problem and to come to a conclusion about, say, what's going to happen next. We also make sure we define a coordinate system, right? At least in the sort of kinematics, dynamics problems we'll be solving throughout this course. Your variables need to find in some coordinate system. I already talked about it a little bit, but we'll see how that plays out. Another thing we're going to be doing that we haven't really done so far as much as we should have, and we'll be working symbolically all the way, right? And that has a number of advantages. One is it makes it a lot easier to find your own mistakes. Like if you end up with an answer that clearly doesn't make sense, working symbolically, you can easily check every single line to find where your mistake is, which is much harder if you just work with a large bunch of numbers. It also has some other advantages, like it can give you certain physical insights into the problem as you're doing the calculation, and we'll come across that not so much here, but in the near future. We're going to make sense of the math, right? The math is this machine that spits out some kind of answer if we apply the rules of mathematics to our setup correctly. But what do those mean, and what if there's like more than one say? What's going on there? Does the math ever lie? It does not, but sometimes it'll be hard to interpret. So we'll make sense of that, or at least we'll make a start. When you solve a problem, always sketch, right? Always try to draw pictures, graphs, whatever is useful to make sense of the situation you're trying to analyze. Never blindly just throw some equations at the problem and hope that something sensible comes out. You need to know what's going on, and then the actual calculation, the math, tends to be fairly easy. But if you don't know what's going on, you're just stabbing in the dark and hoping that the equation you just write down are going to impress your instructor. That's unlikely to happen. And then another technique we'll be using is we're going to check if answers make sense, right? You get to an answer at the end of a problem. Well, are the values plausible? That's one thing we're going to assess. Does it make sense? And then we're going to use a technique called dimensional analysis. We've sort of used it already a little bit just to check that our units effectively are correct of our final answer. Right? Because if the units are wrong, then well, we must have made a mistake somewhere. If the units are right, then we don't know. We might have made a mistake, but we also might not have. So it's kind of a sanity check. that we can do. Okay, but without further ado, let's get started on the actual problem. So here's the problem. Let's take a moment to read through it. And you might want to maybe copy it down and post the video, so you'll have it as we're solving it. And here's the problem. You're late again. Just as you turn the corner, the bus is leaving from the bus stop. You can run at a constant speed, vr, while the acceleration of the bus is a subscript b. So in physics, we like to use subscripts if there's, for example, more than one quantity or more than one point in time, right? You already met like t0 or v0, that's those sort of quantities. We use subscripts to mean, okay, this is some particular, not just any velocity or speed, it's in this particular case the speed of the, I guess R for runner and B for bus, or the acceleration of the bus. Because there might be, more than one object accelerating, the acceleration will be different. We need to be clear what is what. Find an expression for the largest possible distance d between you and the back of the bus, and that's the distance d at the instant you turn the corner and the bus leaves, such that you manage to catch up and jump on the back bumper and still make it to class on time. So don't do this in real life, but hopefully by now you've visualized what's going on, right? You read a problem like this, if it keeps going, you want to stop and be like, okay, can I visualize what's actually happening? Another thing to note, when we've got quantities like VR, A, B, it says it has a constant speed. You might ask, well, what is it? Do we know it? Yes. The assumption here is we're given, right, what that speed is. You can run at a constant speed. That speed is called VR. Now, it's not telling us it's 10 meters per second or 5 meters per second or 100 meters per second. It's just calling it VR, but this is essentially a given, even if we don't have actual values for it. The idea is we express our final answer in terms of those, and then if somebody came along and gave us real values, we could just plug them in and right away would have the problem solved. And to some extent, that is just a sort of phrasing that we can call it, it's part of the jargon of physics. We say you have a constant speed such, the implication is that it's a given speed. Whereas here it says find an expression for the distance d, so we want to relate this to those. So find what is this in terms of those. I think it's fairly obvious, but if you haven't met that sort of phrasing before, it can be confusing. You'll meet it a lot. So hopefully that makes sense. Right? We don't have values, but they're still known quantities for the purposes of our calculation. Alright, so we are asked to find, let's figure out what we're being asked to find. We find the expression for the largest possible distance d, okay, such that we manage to catch the bus. And then it keeps going, I know. If your maximum speed is 5 meters per second, okay, now suddenly we're having values, right? So your maximum speed is 5 meters per second. Oh, you say, okay, well, that is an actual value for this that we're going to use later on. But right now we're being asked to find d in terms of those two. That was the first part. Only once we've done that, we get to plug in some values. Let's have a look. Your maximum speed is 5 meters per second. The acceleration is 1 meter per second squared. Are we going to make it if the back of the bus is 12 meters away from us? So maybe we can already in your mind match what those quantities are in relation to the variables we had up there. But if that is not yet the case, then let's draw a picture. Right? Let's get started. Now, how long does it take to reach the bus again? So hopefully you've had a chance now to read the problem. So here's the question you might ask. I have seen people ask over and over again, what equation should I use? And that is the worst question to ever ask. Because it is not some kind of game where you have, pick the right equation from the hat and plug in the values. That's not going to get you there. It's going to get you into trouble. You can't learn physics by just learning procedures. Oh, this type of problems requires this equation. Like that, people try it over and over and over again because it's is a cheap way. It's a way that seems to okay, I don't actually learn the physics. You just have to know the right equation. It's not going to get you there. You're going to meet a new problem. You have all the tools for it, but you still can't solve it. So don't ask this. And instead you might ask, what is going on? What does it look like? And maybe you can ask, what principles of physics might be relevant here? Or what laws of physics? So those are the kinds of questions you want to ask, right? Not what equation should I use. What equation you should use is going to come naturally out of asking those questions. All right. So let's start then. So the first thing we're going to do is we're going to draw a picture. So I hope you have the problem ready, so you don't have to constantly go back and forth. Right. So the idea is this: we're turning the corner, and there's the bus. The bus is over here. My bus, and it's about to leave. Right, so this is the bus stop. I want to reach the back of the bus. The back of the bus is going to be my reference point. Now I start over here. There I am. Oh no, the bus is leaving. So let's make sense of the quantity. So what do we have? I'm running at a constant speed. Let's note this down. And I'm going to be running in this direction, obviously. Right? So that was the quantity VR. Notice I'm not doing some kind of technical diagram. I'm just noting down on my diagram the things that are going on. So the bus, we know, is accelerating. Maybe I even should write down here constant speed. It's also a constant velocity because we know it's to the right and that doesn't change. Constant speed. Now the bus is accelerating. Initially it has 0 velocity, but then it's accelerating. When things accelerate, sometimes it is a thing, it's a convention to do a sort of double arrow. Not everybody does it, but if you see it, it's meant to say, look, this is an acceleration, whereas this one is a velocity. Of course, an arrow in general could be some kind of vector of another type. We'll talk about it more later. So here's my acceleration. The bus is leaving in that direction. So I want to run, and I want to reach the back bumper. The question is, well, how far can I be away? Right, that's what it's asking us. How far can I be away from the back of the bus? So what we're asked to express in terms of those two is this distance here. This is my distance d. All right. So what does it mean to reach the back of the bus mathematically? Before I answer that, let me just write, to be consistent, constant acceleration here. We said constant speed, which should have done this before. Let me go back to my question. What does it mean for me to reach the back of the bus? To reach the back of the bus, mathematically speaking, it means the position, my position, is the same as the position of the back of the bus. So let's write this out. My position is equal to the bus position. And by bus, my reference point on the bus is the back of the bus. Could have been the door of the bus if I was trying to reach a door. But in a sense, if I'm only aiming for the back bumper here, I don't care what the rest of the bus does. Of course, it's moving with the bus. But in terms of looking at how far is this point away from here, we don't care. Right? We only care about this one point on the bus. Okay, so my position is the bus position. That is what I want to have happen in order for me to reach this. Right? So I've translated the phrase reach the back of the bus into math. Well, have I? Yes, this is math, right? Because these are two variables. Maybe I can write them symbolically. I might write x, r. I think r I chose earlier for for runner, because you're running, right? And that is equal to the position of the bus. That's what we want. Right, we want this to be true. We want this equality to hold. Okay, so let's then write down an expression for each of those. Notice I haven't chosen the coordinate system yet, which is okay, because to say they're in the same position, well, if they're in the same position in one coordinate system, in the same position in all coordinate systems, right? So that is statement that is same. It's not coordinate system dependent. But if I want to find an actual expression for this one and this one in terms of maybe those quantities, well, I need to pick a coordinate system, because I have to use the same coordinate system for both of them, right? Otherwise, this expression just wouldn't make sense. So I think I'm going to want to say this is my origin, like the corner where I'm turning. Oh no, there's the bus. I'm going to make this the origin of my coordinate system, and I have it pointed to the right. I think it's a sensible choice. This is my x. So my x is like a long ruler along the ground in this direction, and there are two positions I'm interested in, namely my position and the bus position, and ultimately I want those to be equal. Okay, so what is an expression for my position? Well, I start here, and let's say at time equals 0 is when I turn the corner. So my position, x, r, and it's going to change with time, right, because I'm moving, so I'm going to have x as a function of time. That is equal to, well, it's constant speed, and I start at 0, so that's just going to be given by VR times t. Right, if I'm running 3 meters per second, then after 1 second, I've run 1 times 3, I'm at 3 meters here. That makes sense. Always do those little sanity checks in your head that the expression you wrote down actually makes sense. Okay, and we're done. Right, that's it. Now, for the bus, we have accelerated motion. Its position as a function of time is going to be equal to, well, it starts from rest, right? So there's no v naught term for the bus, v naught t, but there's an acceleration, so it's going to be 1/2 a bus t squared, right? The displacement as a function of time for accelerated motion. And of course, those two quantities are given. Now, that alone isn't quite true, because the bus is starting here. The bus is not starting at the origin of my coordinate system, right? So at time t equals 0, the moment I turn the corner, the bus is already over here, because that's where the bus stop is. So where is that? Well, it is at the coordinate along my ruler, d, right? If d is 5 meters, then it would be at 5 on my ruler. Don't know what the value of d is. In fact, it's not given in any sense, but I have to add it to the position. That's where it starts, and then, you know, after 1 second, well, it'll be there, plus however far it has moved due to its acceleration. Okay, so I've made sense of what's going on, and that alone allowed me to write down the necessary equations. Okay, so we want those to be equal. We don't care when, for some time, but let's see, let's set them equal. So we want 1/2 a b t squared plus d to be equal to VR t. Okay. So we don't care when the bus, when you catch the bus. We only care if you catch the bus. But that means there is some time t at which you catch the bus. So the question is there some time when you catch the bus? The answer is, well, if this equation here has solutions for t, then that's the time when you've coded it, because that's the time when those two are equal. The answer is if, or let's say yes if this equation, which equation, this equation up here, has a solution. That's not guaranteed. What type of equation is it? It's a quadratic in t. Right. So let's look at it. This is a quadratic. Right. So let's just get it to a new page. So let's write it down again. I.e., the equation is 1/2 AB t squared minus VRT plus d equals 0. So I've just rearranged it to bring it in the sort of standard form of a quadratic. And a quadratic can have real solutions or not real, has no solutions. I mean, it might have imaginary solutions, different story, right? We mean real solutions. So is there some time for which this is true? If yes, well, then that's the time you code the bus at. If not, then, well, you haven't coded the bus. So what determines whether or not this equation has a solution? Well, you should remember that from your math courses. But let's have a look. Let's just write down the answer, right, for the time. Now the time, it's a quadratic equation. You should know the quadratic equation off by heart at this point. It's just one of those things you want to have in your toolbox. It comes up frequently. You don't want to be the guy or girl who has to like look it up, right? You're in the meeting, you've got a high-paying job, you've got to show off, and suddenly you need a quadratic equation. Well, you know, do you have it at your fingertips? It just comes up so much, especially if you were to go in some kind of scientific engineering field. Definitely, by the end of this course, know the quadratic equation off by heart. Anyway, let's write it down. So it's 1/2 times the first term, so 1/2 AB, right? Then minus the second coefficient here, so it's minus VR, and plus or minus the square root of this thing squared, minus VR squared, minus 4 times 1/2 AB times the last term d. Alright, if this looks funny to you, review your quadratic equation. Okay, so let's simplify this a little bit. This is just 2 times 1/2, it's just 1/AB, that is simple. Minus makes plus, then if we plus or minus, we'll make sense of that in a minute. And then the square root, it's VR squared, because the minus signs get squared away. And then minus 4 times 1/2, it's minus 2ABD. Now, whatever the values are, that's going to be some number. That number is real if this thing in here is positive. So need VR squared minus 2ABD greater or equal to 0 for there to be a real solution. Right? If this is not the case, if the thing inside the square root is negative, well, then this would not be a real number. Right? This would be an imaginary number, and the whole time would be complex. It doesn't make any physical sense. So that this would mean there's no time. If this thing is not a positive number, then there's just no mathematical solution that makes any physical sense for the time. Right, so that's the condition that determines whether or not there is whether or not you're going to catch the bus. Right? Because let's go through logic again. If this is true, then this thing is positive, so the square root exists. So that means there is a value when this equation is made true, and this equation corresponded to setting the two positions equal of the running person u and the bus. That's the logic we followed here. Okay, so now if you want an expression, that implies we want that that d is going to be smaller or equal to VR squared divided by 2ab. Now let's do a quick sanity check here. And well, if we run faster, then we can go further. Makes sense. If I run faster, if this thing gets bigger, well then the d is allowed to be bigger and I still catch the bus. That makes sense, right? If the acceleration of the bus is greater, that makes the right hand side smaller. Well, that makes also sense. If the bus is a high acceleration, presumably it can't be as far away. So just a little sanity check to make sure that our answer does make sense. Let's do another sanity check. Let's do some dimensional analysis. Right, this is a distance. This is a velocity squared. Let's just write this down. Dimensional, dim for dimensional analysis. Well, VR squared, the dimensions of that is meters squared per second squared, because it's a speed, a velocity, that's meters per second, that gets squared, meters squared per second squared. We're dividing by the units of the acceleration, that's meters per second squared. So when I divide this by this, the per second squared cancel out, and I am left with just meters. Okay, that makes sense, right? Because I want a distance in the end. Dimensional analysis checks out. Okay, another sanity check we did there. Right, so we did two checks already. We checked. It was a fairly short calculation, right? Probably didn't need to do all of those here. But as a general technique, we checked if this gets bigger, like I run faster. Remember, these quantities are physically meaningful. If I run faster, okay, then I should be able to catch the bus even if it's further away. Okay, that makes sense. This gets bigger, this gets bigger. If your bus has a high acceleration, that makes it harder for me to catch the bus. Okay, this getting bigger makes this smaller. Again, that makes sense. The units of my final answer make sense. They're in meters. Maybe, you could imagine I made a mistake somewhere and maybe I lost the square. Right? Just some, human error along the way going through the math. So in that case, I would have had meters per second divided by meters per second squared. After everything's said and done, that leaves me with seconds. Well, that's wrong. The distance is not measured in seconds. So that would have given me a hint that I'd made a mistake somewhere. It's a really powerful tool, even in some really advanced physics. Okay, maybe we should also plot graphs so we can see in graph form what's going on. So let me just show you what those positions look like. So we are running, right? Let's go back to our earlier motion. So the runner u is running at a constant speed. So we know what that looks like. We're also starting from the origin. So that's this. This is, I should have said, of course, it's a position versus time graph. Right, so this is a straight line. This is the position of the runner. What about the bus? The bus is accelerated motion. It starts from rest. So it might start somewhere here though, because there's a head start, right? So this height here would be the position D. And now it's going to start off slow, and then it's going to speed up and become steeper and steeper and steeper. I do something like this. Right, this would be accelerated motion. Okay. So there'll be 2 times actually when those two cross, and those two crossing means, hey, they're in the same position, right? So when you solve a quadratic, graphically you're finding the points when those two functions intersect. In our case, when this function intersects this function. But you can see that there might have been a situation, let me just do a quick sketch in the corner, where say the bus were started out further away, the same acceleration means the same curve. Starting further away might just mean that it's starting higher up, and it might have looked something like this. Then you would have had no solution, so in that situation you would have missed the bus. Here we would have coded, and the time at which we would have coded would be here. What about the second time? I'll talk about it in just a second, when we plug in some values. Right, so there is a time when you're in the same position as the bus is too far away, well, then they never cross, so you'll never make it. Similarly, if the acceleration of the bus had been greater, it would have curved up like this, up here, and again, the two lines might not have crossed. So there are different ways to analyze the same situation. And maybe we could have drawn those graphs right at the beginning after writing down these and sort of visualize the problem that way mathematically early on. Okay, so we found a condition, and now we're actually asked to plug in some numbers. Let's go back to the problem for a second. Our maximum speed is 5 meters per second. Our acceleration is 1. D is 12. Are we going to make it? Well, that's going to be easy. We're just going to apply what we just figured out. Right? We had that D has to be smaller or equal to VR squared divided by 2AB to catch the bus. Well, let's have a look. Let's plug in the values we're given. We have, is D in our case is going to be 12 meters. What's V squared? V is 5, right? So VR is equal to 5. AB is equal to 1. Those are the values we're given. Oops, what am I doing? Meters per second. 1 meter per second squared. So those together imply that VR squared over 2AB comes to 25. 5 squared divided by 2 times 1. So it's 2, that makes 12.5 meters. Indeed, 12.5 is greater than 12. So 12 meters is smaller than 12.5. So we catch the bus. Just, right? If it had been 1 meter more further away, we would not have caught it. Okay, and it's asking us when did we? If so, right, I guess it's kind of a hint that we're probably going to find it, catch it. Why else would I be asking this? Unless we're being really tricky. So how long does it take you to reach the bus? Well, we just now have to find the time, right? How do I figure this out? Oh, I just need to actually plug in the values to find the time. Well, we found the answer earlier, right? This is the time. We just never care to actually evaluate it. Well, now we just evaluate this to find the time. So we had, so when? Well, we had that that t is equal to 1 over the acceleration of the bus times VR plus or minus the square root of VR squared minus 2ABD, and we know the thing inside the square root is positive, right? So let's plug in the values. In our case, see, we're plugging values now, not earlier when solving the quadratic. Like, we figured this out. Now we're plugging in values. That's 1 over 1, because AB is 1, times 5, plus or minus, okay, what's going to be in the square root? It's 25, 5 squared, minus 2 times 1 times 12. Well, this is 24, so 25 minus 24 is 1. 1 over 1 is 1. It works out rather nicely. I have to get 5 plus or minus 1. So that means we catch the bus after 4 seconds, 5 minus 1, and again after 6 seconds, 5 plus 1. Okay, so obviously this is physics, right? So we are running, we're going to jump onto the bus when we reach it after 4 seconds. So this is probably the answer we actually want. But what happens at 6 seconds? Why does the math give me a second answer 6 seconds? Well, if you imagine you're running faster than the bus, let's look back at our graph here, right? We're running, we're catching up to the bus is speeding up, but it's not going fast enough yet to get away from me. I'm still faster. So while I'm here, while we're between those, in our case this was 4 seconds, this is 6 seconds, right? Those are the solutions we found. During that time interval, we are at a higher position than the bus. So we are actually ahead of the bus, ahead of the back of the bus. But then the bus keeps speeding up, and so it goes past us. So during this time, we're sort of by the side of the bus. If we didn't jump onto the back bumper here and stop the whole thing, right? If we kept running, we'd be next to the bus because we are at a position that's great, at a higher value, a greater, position value than the back of the bus. So it's down here. We are up here at, this particular time down here. But then, because the bus keeps speeding up and we're going at a constant speed, eventually the back of the bus is going to overtake us again, which gives us a second chance to jump onto the back of the bus. So maybe if you wave at somebody inside the window, you might, keep running, and then you wave at them, then in the last row you wave, but then the bus keeps speeding up, and then you decide to jump on the back bumper. Right? So that's the 6 seconds here. The math spits it out. The math does not lie, right? But you have to think about, well, what does this answer mean? Which one is the answer that I actually want? And in this case, that would be this one. And there it is. We've solved the problem. So it took us a bunch of pages, but we were making very detailed notes, right? There wasn't actually that much calculation. The only calculation was to really solve the quadratic. You have to set it up, you have to understand what's going on, and then the rest is just understanding how to interpret what we're seeing. That is the great part of the art and the craft of doing physics. Now, before I leave you, let me come back to what I showed you earlier, where I said never ask what equation should I use, right? But what equations did we use? Well, certainly we had math, right? We had the quadratic equation and so on. But here's, in terms of actual, like the stuff we've done, the sort of relationships between motion, all we'll ever need and that is in 1D kinematics, although to some extent also in 2D kinematics, is what is acceleration, which is that A is the rate of change of acceleration, of velocity. Now I'm writing it down like this. I could have written it as a derivative. That would allow me to deal with non-constant accelerations. For the most part, in this course, we're going to deal with situations where at least the acceleration remains constant. Like the bus had a constant 1 meter per second squared. That value wasn't changing. In general, we can deal with changing values if we treat this as a proper derivative. And maybe I'll make a separate sort of bonus video about that. What is acceleration? And the other thing is just the displacement for accelerated motion. And that is that your change in position is equal to your initial velocity times time plus 1/2 a t squared, or you could write delta t to mean that a change in time. Again, you know what it means, you need to know how to apply it in the situation, not worry about is it t or delta t, what's the correct form. Right. Notice that this is delta x, the change in position. For example, in the case of the bus, this wasn't there, but this was there, but then because this is a change in position, but the bus already started somewhere that wasn't 0, we of course had to add that to get the actual position along our imagined ruler. So those will solve you everything. Everything else, like I said before, is something that is derived from those. So that equation with the v squared, v final squared is v initial squared plus 2ax, a delta x. Sure, you can derive it from those two. Useful, but you don't need to think of it as this giant zoo of equations and you got to find the right one. No, there's those two. Everything else follows, everything else is applying those two correctly. So I hope going through the problem very slowly and carefully, explaining my thought processes, writing it all down, I hope that helped. But the only way you're actually going to learn this sort of stuff is by doing it. So now, close down the video and get working. I'll see you soon.